Right, here's a nice worked example. It's an exponential modeling question, so it fits into the sort of exponent log category, and also in the modeling in the modeling topic, which runs across a number of different types of models. Let's have a look. The number of radioactive atoms N in a sample of a sodium isotope after time t hours can be modeled by this equation: N equals N0 e to the power of minus KT, where N is the initial number of radioactive atoms and K is a positive constant. Remains valid for a large number of atoms. Okay, so we kind of recognize this form, and we would say that the relationship we're looking for is between N and T, and the unknowns in this are N0 and K. So K is a measure of the sort of profile. So if it's negative, because K is a positive constant, then negative K will be a decay. So we've got this shape here where it's sort of asymptoting down to y equals 0, or f of x equals 0, and if K is bigger, then it's going to be more stretched out. Or in fact, if it's going to be smaller, it's actually more stretched out in the direction of the t-axis. Right, so we'd say there are two unknowns here. Normally we'd be expecting two boundary conditions to resolve for those. However, we're only given one boundary condition here. If we read down a little bit, it says it takes 15.9 hours for half of the sodium atoms to decay. Now that's your lot. That is it. So we're not actually going to resolve for the two unknowns N0 and K from the one boundary condition. But in actual fact, in this problem, this is quite an interesting problem, because we're actually not interested in the number of atoms initially, because the questions that were being asked really are about the proportion of atoms left after a certain amount of time. So in a sense, our variable we could think of as being N divided by N0. Okay, so that really then leaves us with just the one unknown, which is K. So let's see how this works then. We've got this boundary condition, which is it takes 15.9 hours for half of the sodium atoms to decay. So the 15.9 hours, N0 divided by 2, half the size, equals N0 e to the power minus K times 15.9. Right, okay, so we can cancel the N0s. If we reciprocate both sides of the equation, so that half becomes 2, this minus e to the power minus stuff becomes e to the power of 15.9K. And then we have to, we want this K from the argument of the exponential function to be on the subject line. So we take the natural log of both sides of the equation, and that means we've got natural log of an exponential, inverse function and inverse. So that's equal to 15.9. And the rearrange and use our calculator on that, we get K equals 0.0436. That's to 4 decimal places. So our resolved equation is this: N equals N0 e to the power minus 0.0436 T. So it goes on to say, determine the number of days required for at least 90% of the number of atoms in the original sample to decay. So what the question we're asking here is, when is the number of atoms N equal to 1/10 N0? Okay, so with that substitution there, N equals 1/10 N0, we can plot that into our relationship here. And again, the N0s cancel. If we then reciprocate both sides of the equation, we get this. take the natural log to get the t function on the subject line, then rearrange, and t equals 52.812 hours, which is giving us 2.2 days to 1 decimal place. So that is that. Right, so let's just wind down a little bit. Okay, so part B says find percentage of atoms remaining after the first week. Give your answer to 2 sig fig. Okay, well, the fraction remaining, let's do the fraction remaining, and we can do percentage from that, is going to be this ratio of n to n0. And that, of course, if we go back to our equation here, n divided by n0 is going to be equal to e to the power of minus 0.0436 times t being 168, there being 168 hours in the week. Okay, so we can just calculate this. This is just sticking this into the calculator. This is going to give us 6.6 times 10 to the power minus 4. That's the 2 significant figures. If we want a percentage, we can multiply that by 10 to the power of 2. And this is going to give us a percentage left of 0.066% to 2 significant figures. So after a week, it's kind of, not much of it left, basically. Right. Okay. Now the other 2 things is they're only 1 markers, but actually, in this case, they're not completely obvious. Or I don't think. Part C says explain why the model can only provide an estimate for the number of remaining atoms. Well, yeah. There's 2 things really. I mean, first of all, we don't know the initial number of atoms, so you know, we've got to have something in order to actually say what the value of n is. So we need some other assumptions in there in order to do that. I mean, the other thing is it's just a model anyway. It's you know, models are really built as they're generally speaking an approximation of what's going on, because there are also other factors involved that we don't include in our model because of complexity. So either or both of those things together probably would do that answer. And why is the model invalid in the long run? In the long run, it says the model remains valid for large numbers of atoms, and of course you're reducing. So eventually, by the statement in the question, it's not going to be valid. But ultimately, we're just going to we're just going to have 1 atom. So at that point, and this is not about splitting the atom. Basically, once you've got 1 atom, then it either stays the same or becomes 0. So eventually there remains just 1 atom, and you know, add your own text on there to qualify, I think. Okay, so I think that's kind of quite an interesting example, one to watch out for. You know, in that we are, you know, we've got 1 boundary condition for what is ostensibly 2 unknowns. But if that arises, then say don't panic, you know, because if you're being asked for percentages of reduction, you know, half-lives and things like that, then you know, that's will probably be sufficient to do the job. Right. Okay. So hopefully that's been a useful example, and thanks for listening.